Today, I'll focus on carbon capture and storage. So, I mean, obviously, one of the things we have to do in this world is to supply the energy services that we're providing now and that we pretty much all take for granted, and do it in a way that has much lower emissions. And then we also need to think about the part of the world where there still is an additional need to supply energy services that make modern lives possible and comfortable and healthy. So the question is, okay, how do we do that? Well, there are some parts of this that you can really see the elements of the transition already. That is that, for example, we're, I think, going to electrify a whole lot of transportation as we go forward. But some of the parts of transportation are hard. And one of those things that's hard is airplanes. They're at least right now, it's hard to imagine a battery-powered airplane that can fly very far, just because of the fact that batteries, in a battery, you carry around all the reactants, both sides of the electrochemistry. But if you burn fuel, then the heavy parts of the product molecule, CO2, the oxygens, they come from the air, and you don't have to carry that around in the airplane. So that's hard to deal with, and for at least some transition period, we're going to need some other way. The other pieces of this are, for example, iron and steel and cement. When you take iron ore is an iron oxide, and when you strip off the oxygens, you're left with the metal iron. Stripping off the molecule, the oxygens right now is done with carbon. So that inevitably adds CO2 to the atmosphere, plus whatever heat it takes to heat everything up. Now, can it be done other ways? Sure. You can do it with hydrogen, for example, though that has to find its way into the marketplace. And there are some metallurgical issues as well. And then the last bit is load following electricity. Massive deployment is of wind and solar, for example, maybe some more hydro, and then some more exotic versions. But basically, big deployment of wind and solar implies that you have to deal with the intermittency of wind and solar. Sun doesn't always shine, wind doesn't always blow. So now batteries might be one way to do that. They tend to be more expensive than something like pumped hydro. But having a dispatchable element, something that you can decide when to use it and turn it on, that's also clean is a possibility. And carbon capture and storage enables at least one pathway for that. So here's one possible, this is the International Energy Agency's guess at how one way that you might do this. Now, this sort of implies that there is the way, and no kidding, this is a complicated, diversified system. But the obvious elements are a big dose of energy efficiency. We need to be efficient in the way we use energy in absolutely every possible way we can do it. Lots of renewables, some moving from coal to other kinds of fuels, some nuclear. There's some, you will see how the nuclear has had a hard time competing on cost. But on the other hand, Microsoft just apparently set up a deal to reactivate a mothballed reactor at 3 Mile Island. And then lots of other things, but plus a modest amount of carbon capture and storage. And the reason for that is just really to attack those hard to decarbonize systems. And I'll say more about direct air capture in a minute. Well, I talked about the intermittency part of this. This is a picture of California hourly wind and solar in 2017. And it kind of one of the things that you see is that there are a whole bunch of extended periods of where the combination of wind and solar is likely not enough to supply the full demand. Now, short term, you can certainly do some of this with batteries, and the mention of 20 gigawatts of batteries. Now, there are two things that matter in a battery. One is how much power you can deliver. That's gigawatts. The other is how long does it last, and that's gigawatt hours. Typically those are aimed at the short term, the evening ramp in power requirements, for example, as the sun goes down. So it's the long duration storage that is the issue. And of course, one way you can do that is with some stored resource. Could be hydrogen stored, or it could be methane that you burn with carbon capture and storage. So then the last bit of this sort of why do we care about this is the question of uh, what happens if we don't move fast enough? And right now, at least, we don't appear to be moving fast enough in terms of CO2 that we're putting into the air. So one possibility, at least, is to to look for negative emissions, to try to capture some of that CO2 that's in the air and put it somewhere. And I think there's a segment of the research community that says, gosh, we need to be thinking about this because we aren't really moving fast enough along the way at the moment, at least. Why do we do this? Uh, well, I talked about the hard to eliminate emissions, carbon removal. One thing that a whole bunch of studies show now is that if you have a modest amount of dispatchable power, then that's clean, then it's a much cheaper system than one where you build a whole lot of excess capacity in, for example, wind and solar, and then don't use part of it, a segment of it in time. And so this is what comes from diversifying the energy supply system. And there's much to be said for having a diversified system because not only is it cheaper to build, it's also more resilient in the face of disruptions of one kind at all. And then the last thing is that a bunch of this we can do now, even as we put in place the stuff the other bits. So what does it take to actually do this? So there are four parts. One, you have to separate the CO2. I mean, you don't want to have to deal with any more of the stuff you have to store than necessary. So
capturing the CO2, separating it, for example, from combustion product gases or from whatever process produced the CO2 is the first step. You need to compress it up to pressures that are high enough to put it somewhere. We're going to talk about geologic storage. So as you go down in the Earth's crust, just as if you swim down to the bottom of the swimming pool, your ears hurt at the bottom of the deep end, right? Because of the weight of all that water above you. Well, you can think of the Earth's crust as mostly filled up with water. So as the deeper you go, the higher the pressure. So you have to compress the CO2 enough to get it to go in. And that's actually good because that reduces its volume as well, increases the density. So that's an important step. And plus, you're going to need to move it someplace in a pipeline, and you'd rather do that at high pressure just because then that changes the volume of the pipeline. And then the last thing is to put the CO2 someplace. Okay, so first of all, maybe the most important thing to remember about CO2 capture is that the lower the concentration of the whatever mixture, the lower the concentration of CO2 in whatever mixture it is a really important thing. And why? Because the jelly bean example is one where if you have a pot full of jelly beans and you have to just go find I don't know, the green ones, the more you have to sift through to find the few green ones, then the more effort it is. Well, that's true thermodynamically as well. And if you look at the energy that's required to do the the uh, the separation, it depends quite strongly on the mole fraction of CO2. Obviously, if it's 100% CO2, the mole fraction is 1, and it's already separated, so you don't have to do any additional work there. But if you look down to for example, in a pulverized coal plant, the concentration of CO2 in the combustion product gases is maybe somewhere between 10 and 15%. It's in a natural gas combined cycle power plant, it's 5 to 8%, say. And in the air, it's 400 parts per million, but that's 0.04%. Okay, so it just is a whole lot more effort to thermodynamically capture the CO2 if you deal with air. And one way to think about this is you have to blow a whole lot more air through whatever device you're using to capture it, and that the fan loads for that, for example, are part of the energy requirement. Okay, so so that means that you go look at sources now. Right now, for example, if you make ethanol, or then there is a nice, almost pure CO2 source there. If you do, today we use ammonia in very large quantities for fertilizer. We make the hydrogen. I know Diana will talk about hydrogen coming from. It's mostly made from methane, but they have to separate the hydrogen then from the CO2. So the separation is done, but it's already been done in order to sell the hydrogen. The other place that happens is in natural gas production. So some natural gas has some CO2 in it. In order to sell the natural gas, they have to do the separation. So separation's already done. So then you would take, those are the sources you'd go for first because they're the least expensive. But of course, if we don't do enough of that, then the air is also a possible source. And the estimated costs of these things correlate pretty well with the concentration of the CO2. Now, can we do better? For sure. The mention was made of the folks that there are a lot of people working on good ways to separate CO2, and you know, in a way, there's a kind of an unalterable conflict here, because what you'd like is some stuff that glums onto the CO2 quickly and easily, and then you separate that somehow, and then you have to get the CO2 off, but you want it to be easy to get it back. And the better it glums onto the CO2, the harder it is to get it back. So so there's like all engineering, there's a trade-off there. So, but we actually have a lot of experience with this. Large quantities of CO2 are separated every day when making hydrogen as natural gas separations. It can be done with virtually any combustion stream. And in fact, there's an operating plant in Canada that's a coal-fired power plant where they capture the CO2. And basically what happens is that they burn the CO2 in the boiler here, and then they make steam that turns the turbine, and then the CO2, nitrogen, and water vapor mixture goes off to a chemical system that I'll show you in a second that separates the CO2. So here's a picture of it. And basically the way this works is that the flue gas comes in the bottom of this tower. You can see it's over on the right side. It has the label flue gas and MEA above. MEA is a monoethanolamine. It's just a mixture of water and a solvent that has amine groups on it, and that glums onto the CO2, and then what goes out the top has a lot less CO2, and then you take that, you separate the liquid, take it over to the other tower, and then heat it up to drive off this CO2. So you can just see now this solution does a pretty good job of hanging on to the CO2. It gives up lots of heat when that happens, so now you need to manage the heat transfer back and forth to take advantage of it. You don't want to waste all of that. So that you can see that it takes lots of pipes and pumps and stuff to do this. This is done at commercial scale, very large commercial scale around the world every day in refining operations and natural gas separations. So there's a picture of it. It's a big coal-fired power plant
But this bit over on the side is that's the carbon capture plant. So they're not doing the whole plant, they're just doing part of it. But it definitely can be done, and it definitely works. And you might ask, well, why the heck don't we do this, you know, around the world? And the answer is cost. Until recently, in the United States at least, there was no good way to capture to recover the cost of doing that. So instead, the combustion product gases were evented to the atmosphere. Now, with the passage of the Inflation Reduction Act, now there's an $85 a ton tax credit if you capture the CO2 and store it. So that has spawned. You'll see toward the end here that spawned a lot of activity in projects. Although, to be honest, it's coal. There's enough other stuff in the combustion products for coal that it's a lot easier to do it with natural gas, even though the concentration is lower. So here's an example of a way you could do it with natural gas. There's a little demonstration power plant outside Houston, in the little town where I was born, as a matter of fact, Baytown, that does this. And this burns natural gas, but they do it with pure oxygen. So the pure oxygen then makes CO2 and water. That mixture at high pressure and temperature drives the turbine. That makes the electricity. On the downstream side, you cool it down. That knocks the water out, and then that leaves the CO2, which you compress back up to pressure and circulate it back. So the working fluid for this turbine is circulating CO2. Now you can't keep adding CO2 forever here. You have to take some out, and you take it out on the high pressure side. And what that does for you is to provide the CO2 ready for injection into the subsurface or transportation to wherever the storage is. And the additional cost of capturing the CO2 is very small. Okay, the price is paid by separating nitrogen from oxygen. So thermodynamically, no free lunch, folks. But then there is a market for liquid nitrogen and a market for liquid oxygen. Now, how that would work if you did this at big scale, more to think about there. But certainly can be doing it. Advocates for this think they can do that at a price that's competitive with a new combined cycle gas plant. So that's and there are starting to be investments in plants like those around the world. So let me just say a word here about the direct air capture. The picture on the right is the artist's conception. Guess might be a better word of what it might look like. You can see it's a lot of blowers and a lot of fans. So if you were going to do this at big scale, it takes a lot. And they basically kind of do a sort of complicated chemical process, which I'm not going to take you through all of it. Basically, potassium hydroxide absorbs CO2 pretty well, and then you can take that and turn it into calcium carbonate. You make potassium carbonate, that you can turn that into calcium carbonate. Calcium carbonate is limestone, right? So then, and if you heat that up, then you can drive off the CO2 and make calcium oxide and recycle all the bits and pieces. Now, that is the heating up the calcium carbonate is what you do when you make cement, for example. Can be done, has been done at pilot scale. There's a plant being built in West Texas to do this now and inject the CO2 there for oil recovery. With the idea that you inject more CO2 than it takes, than you're going to get from burning the oil. So the idea was that you're going to make oil that has zero carbon, so zero carbon emissions. So in any case, it can be done. There are lots of people working on all kinds of different versions. There's a Swiss company called Climeworks that does this with a porous bed of particles with coatings of amine stuff. There are many variations on themes like this, so definitely can be done.
Why don't we do it at scale? Well, cost is the big issue. So the pipeline transport of the part of this is well worked out. When I was a fledgling engineer in the early 70s, I worked on a project in West Texas that was taking natural CO2 down from the Four Corners area for injection into the oil fields to recover oil that would be left behind by conventional techniques. And those pipelines got built, and they've given a lot of experience. This picture shows those orange wiggly lines in Texas and New Mexico and Colorado and Wyoming are existing pipelines, and there are a bunch of others. The blue ones are ones that might be built to do capture CO2 from a bunch of existing sources and take it to somewhere in Texas where there's lots of porous rocks to store the CO2. The other possibility is being built in Europe. It's a system that separates CO2, puts it on a ship, and then transports it to basically the gas fields in the North Sea where it can be injected into the subsurface. So that's more speculative. The pipeline stuff is well worked out. So now we need some place to put the CO2. If you think about it, you know that there are rocks that contain buoyant fluids because we have oil and gas reservoirs. So in an oil reservoir or gas reservoir, rocks that have organic material have been buried deep enough to be cooked that cooks out the hydrocarbons. Those are buoyant compared to water in the subsurface, so they try to float to the top. But they can be retained by low permeability rocks known as seals that retain those buoyant fluids in the subsurface. So what you do is you look for places that have porous rocks that have room for the CO2, but also have the right kind of seal rocks over top so that they won't leak to the surface. And there's a lot of experience, of course, in the oil and gas industry of how to look for that in the subsurface. So then you say, well, okay, where might we put them? Well, one obvious place is depleted oil and gas reservoirs. The pressures have been pulled down. There's less chance of induced earthquakes as you push the CO2 in, and they've been doing this for a long time. So those are places that are obvious possibilities. The CO2 now is used for oil recovery and operations. So you could either continue that, or you could stop the recovery part of it and just inject the CO2 into the formations. But if you're going to do this at really big scale, then you want to do it in rocks that contain salt water. Okay, so CO2 would just push the water out of the way. You do have to worry about managing the pressures in the subsurface, but at the same time, the physics and the flow modeling is all well in hand because of all the years of understanding subsurface flow for oil and gas. So for example, if you think about, well, so you might know that the Central Valley out in California has about 30,000 feet of sediment that eroded off the Sierras and filled up this basin, and it's got layers in it, and the layers have sometimes when you have big floods and storms, you get these fine grained rocks that are mudstones and clays and that sort of thing, and those restrict the vertical flow. So you can go look for places there, and sandstones interbedded with shales are a possible location where you might do that. So you might say, well, okay, what happens if as we get to doing this? Well, obviously you need the seal. CO2 dissolves in water, as anybody who drinks fizzy water knows. And so if you wait long enough, the CO2 will eventually dissolve. And the interesting thing about CO2 in water is that this still surprises me, that the water that's saturated with CO2 is more dense than regular water, and it's certainly more dense than the CO2 in the separate phase. So
So somehow those CO2 molecules and the water molecules can kind of snuggle up together in such a way that it makes a mixture that's a little more dense. Not a lot more, but a few percent. And what that means is once it's dissolved, the driving force is to go down, not to go up. So, so that can help trap things. And then if water flows past the CO2, then it causes the CO2 to break up in little bubbles in the pores. And once that happens, it's really hard to move the CO2. So there are ways to make sure that happens. And then some rocks react with the CO2 to make solid minerals. That's mostly not true for the sandstones, but in basalts, for example, in volcanic systems, they do react. There's a place in Iceland where that's being done now. So you can see what you do is you find a good seal up on top, you inject the CO2, and then it flows along under the seal and then dissolves, making a system that then where these denser fingers slide down through the salt water. And there's been lots of those of us who like to solve differential equations have had a good time with all of this. We've worked on the hydrodynamically unstable flows in ways that where we have a good feel for how they work. But it does say that you have to have that seal because this doesn't happen overnight. It takes time for all of this to happen. This is a modeling study of all of that. So, okay, so if you're convinced so far, then the next question to ask is, all right, where might we put this stuff? And the most likely answer is sedimentary rocks. And the reason sedimentary rocks are just things like sandstones, which are just collections of a whole bunch of little tiny particles stacked up on top of each other with spaces in between, pore space that is someplace for the fluids to reside. In many places, that's water or salt water usually. In some places, it's oil and gas, but there are a lot more places that just have water. So if you look at the kinds of rocks that might be possible, the dark gray here is a good, not every rock here is going to be possible. You don't want to do this in a city or a national park, for example. But there is a lot of this kind of rock. So that's not likely to be the kind of limiting situation that will determine what we do. We do have some experience in doing this. This field is actually out in the North Sea. It's a place where Norway for a long time has had a carbon tax on emissions offshore. There was CO2 in the natural gas, so the CO2 got separated from the natural gas. Natural gas got piped ashore, and the CO2 got re-injected into a sandstone lying above the CO2. And this has been going on since 1996. So there's a lot of experience here. This is the sort of thing that you can see using seismic signals. So you make basically a vibration signal, and then that flows through the rocks and bounces off the density, places of density differences. This is used in natural gas exploration and oil and gas exploration, and also to detect nuclear explosions around the world, or sometimes you can do this with earthquakes as well. But in any case, here you can see the pictures over time of the plume of CO2 contained in the subsurface. Here's a place in Illinois. This is CO2 that's been captured from an ethanol plant where they've been injecting CO2 here, and it's now gone to bigger scale. Now here, this is a place where they did actually have a leak to a formation above, but it was a leak in a well. So wells are the most likely leak paths, and of course we actually know how to fix wells if you detect a leak. So one of the things you have to do here is to monitor carefully to make sure that it is not leaking to the surface. And then the last thing I would say here is that if you take a molecule of methane and oxidize it to make CO2, then the CO2 is always more dense than methane at the same temperature and pressure. So in principle, at least, you could take that molecule out of some natural gas reservoir, bring it to the surface, make your electricity, and then put it back and have volume left over. Okay. Now, is anybody doing this? No, because it just hasn't been cost effective in the past. But it certainly could be done, and there are lots of places where, in that case, what you would do is you would locate the power plant near the gas field and then use the transmission and distribution system to move the electricity. So lots of possibilities. You might ask, well, can we do this? And that slide from the International Energy Agency said 3 billion tons a year. These are very big numbers. So if you just, now, do we engineer stuff at this scale? Absolutely we do. Look at all the water handling systems, the sewage injection into the subsurface, and then the oil and gas industry. But if you convert that CO2, that billion tons a year, to the goofy units that the oil industry uses, barrels per day, then 1 billion tons a year is about 35 million barrels a day. The oil, the world uses about 100 million barrels a day of oil, because that's liquids, and some more volume. So do we engineer stuff at that scale? Absolutely we do. But 3 billion tons a year is a pretty big amount. So for sure, this can only be one element that you use judiciously in places where you don't really have other good options. So, and there are plenty more details to think about, all the safety issues. You want to make sure that you protect groundwater, that if you inject too hard and too fast, you can make local earthquakes, and you don't want that to happen either. So a monitoring system that helps you deal with that is, and then the other normal kinds of environmental systems have to be dealt with as well. These are industrial scale systems, and so this is not something you want to do in somebody's neighborhood. It needs to be in places that are suitable. And of course, we want the stuff to stay there. Now, if asked, I would say, look, it is certainly possible to, with good site selection, good engineering, careful monitoring, and quality operations, to put CO2 in the subsurface and leave it there indefinitely. That absolutely can be done. So we just need to if we do this, we need to make sure we do it. Now, I mentioned briefly the Inflation Reduction Act. That has triggered a whole bunch, a big growth. And if there's a lot of information on this slide, but this little, the stacked bar diagram, that's the number of projects that were in construction, operations, or planning as of 2023. The big jump the next year in 2024 gives you an idea of how much activity has been induced by the fact that there's now a way to recover some of the cost of doing this. So we'll see how all that plays out. So I will stop here just by saying that we have the elements that are needed to do this well enough along that we could do this at a scale big enough to matter, and so we're going to see whether how that goes.